Let's see, we're a little bit early, but I'll show you a demonstration of something from last week, which is the force on a current, although in this case it's a force on a magnetic field that is kind of causing it. Or let's see, I guess it would be the torque on a current loop in an external magnetic field is what it happens to be. And it's a primitive version of a, oh, I didn't click share yet. I think I did, maybe not. Can you see the guy standing in front of the classroom? One of the videos?
Yeah, we can.
Okay. Anyway, at big universities like University of Washington or University of Minnesota, they will have a person whose job is to build and fix and maintain the demonstration equipment that they use in the large lecture halls. And I wish I had someone like that. But anyway, they will have all kinds of neat stuff that is kind of fun to look at. But this is a demonstration of a primitive electric motor, except it's the basis for an awful lot of DC electric motors. And so you can see how this thing works. Let's see, I need to bounce back to the start of it, I think.
Next, I'd like to demonstrate the application of a magnetic force to a simple motor. Here I have a demonstration motor which is wired up to a battery and a switch in such a way that the current goes through the circuit and passes through each of these coils sequentially. It goes back through the switch and back around to the battery. So I have a current in these two coils, and we can think of the current in each of these coils as creating a magnetic field in this region of space, and then the current in these two coils here in that magnetic field will experience a magnetic force. Again, moving charge in a magnetic field experiences a magnetic force. That force gets translated to a torque, which tends to make these two coils tend to line up in that fashion. But what we do is we play a trick on it. Just before those coils get to that position, there's a split here in this ring, and that causes the current to reverse. So a little bit of inertia carries it past, and then the torque is such as to make it line up this way. And then we reverse it again. So it wants to line up this way, and then this way. And so it just keeps right on going around in that fashion once it gets started. And that's the simple DC motor or direct current motor, demonstrating the nature of the magnetic force and the application of the magnetic force to a practical device like the electric motor.
That's kind of neat. I've got some really crude motors like that out at school, but they rotate so fast that you can't really tell what's going on. But that one's, and they're also not that small, but they do have the split in the thing, so the current reverses direction, and it depends on some inertia of the rotating object carrying it past that equilibrium point. Yesterday, let's see, I completely forgot about doing a makeup test. I was waiting to hear back from someone as to when it might be, so I'll send out an email today, a message, seeing if there's some time this afternoon or evening when we might do that makeup test. This is the makeup for test number 1. And let's see. Yeah, watch for that shortly after 11:30 maybe is when I could send that message out. Anyway, today I wanted to start with just a couple more Ampere's law problems where we'll apply things that we knew about that. And then let's see, there are a bunch more demonstrations by these guys that I want to show that are an introduction into our next section. Will be chapter 29, which is on Faraday's law of induction. And what do they call that? They just call that chapter electromagnetic induction. But Faraday's law is one of the things that governs that. And so we'll take a look at that. And they're kind of fun demonstrations. I've got similar things for a lot of these demonstrations out at school, but they probably have fancier versions. Anyway, start off with this problem. And actually, I'm going to drag something over here. This is our formula sheet for this quarter, and you haven't had a test yet where you use the magnetic formulas yet, but in the center column here, there's Ampere's law and applications, and you can see Ampere's law there, and then it's got the formula for the magnetic field on the axis of a solenoid, and then the field within a toroidal solenoid winding. And a toroid is a solenoid that's been bent into the shape of a circle. And so you can see that. Let's see, Faraday's law of induction, that's the next section we get to. Fun stuff. It's got a time derivative of the flux of the magnetic field in it. And so it's like abstract concept on abstract concept on abstract concept, and pretty neat stuff. But anyway, we'll start with this problem. And I don't know why, but my light don't seem to be lighting it up a whole lot today, but that's okay. Should still be legible. Okay, so you're a new electrical technician working somewhere, and you're designing a large solenoid, and you want to have a uniform 0.150 Tesla magnetic field near the center of it. And that's, I don't know, 15% of a Tesla. That's a relatively strong magnetic field. And you have enough wire for 4,000 circular turns. It doesn't say what the gauge of the wire is, but we'll not worry about that. And the solenoid has to be 1.40 meters long and 2.80 centimeters in diameter. What current will you need to produce the necessary field? Well, this is the formula for the magnetic field near the center of a solenoid. And we happen to know what B will be in this case. We know what mu naught is. We're trying to figure out I, but we need to know the number of turns per unit length, which is what N is. Well, we're going to have 4,000 circular turns in a 1.40 meter long solenoid. And so the number of turns per unit length is just going to be that ratio, 4,000 over 1.40 meters. So we can get a number for that, or just save this and stick it into there. In fact, we can do that. I will equal B over mu naught N. And so we want 0.150 Tesla, which is a Newton per amp meter. Let me keep that in mind. Mu naught down here is 4 pi times 10 to the minus 7th. Let's see, got it on the formula sheet, newtons per amp squared. And then N that goes down here is going to be 4,000 divided by 1.40 meters. And the 4,000 turns, that's just a placeholder word. It doesn't actually have any physical dimension. And I'm just going to remind myself that a Tesla is a Newton per amp meter. And on top, I've got a Newton and a Newton. Those will go away. I have a 1 over a meter there and 1 over a meter there. They'll go away. On the bottom, I've got 1 over amp squared, and on the top, I've got 1 over amps. I'll end up with amps when I flip that bottom fraction and bring it up on top. So dimension-wise or unit-wise, we're just fine. Not a terribly hard problem, although it's hard to keep track of all these formulas we've got going here. Hope I got all this right. I get a fairly hefty current of, I don't know how many sigs we've got on this. Usually things like turns you can count to the nearest integer, but who knows? I would guess probably a couple, but I get about, well, if I only have one significant figure, I would get 40 amps. So this had better be fairly hefty wire. You wouldn't be able to use number 30 gauge wire or 30 gauge wire for something like this. You'd vaporize this stuff. So anyway, you'd better have, you know, maybe 10 gauge copper wire, something like that. I think we did a problem yesterday where we were using that gauge of wire. I don't remember, but at any rate, that's a plug and chug problem for just using that particular thing. This is another one out of your book. It's about a coaxial cable, and you don't see them so much anymore. They used to be the things that you would plug into the back of a TV set that you would then connect to your cable thing coming into the house was a coaxial cable. And it's one that has a conductor running down the center of it. And then usually there'll be some plastic filler between the internal conductor. And then on the external conductor, a lot of times it's just braided copper wire for that outer shell. And then there would be a layer of plastic insulation outside of that to protect the thing. But the braided copper wire would be set to ground. And so if you happen to get a nick in the wire, you're not going to electrocute yourself with 120 volts or whatever it happens to be. But the signal then would run down the center one. But in this case, we've got a solid conductor in the center, and it's carrying a current that in this case is heading in that direction. And then the outer conductor is carrying a current in the opposite direction. So this is providing both paths for the current flow, the outgoing current and the return. The current are distributed uniformly over the cross sections of each conductor. And what that means is that we'll have cylindrical symmetry or axial symmetry in this case. So we want an expression for the magnitude of the magnetic field at points outside the central solid conductor but inside the tube. So if we drew a picture of this, we've got a few different circles on here. There's the center one. That could be the center conductor. This could be the inside of the solid conductor on the outside, and this could be the outside of it. So this dimension is A. This dimension is B, and then that thing happens to be C. And so we're just supposed to find the magnetic field within this region here, and then within this outer region here. So that's all we have to do. And we can use Ampere's law for that, because this is one of those few cases where we actually have some axial symmetry where we can use it. And that's really about the only time you can. So Ampere's law in this case is the integral of V dot ds around some path will equal mu naught times I that's within the path. And for part A, the I that is within the path is this current I that's coming out in this direction. Now, to get the direction of the magnetic field due to that wire, point your thumb of your right hand in the direction of that current, which in this case is out of the page, and your fingers will curl in the direction of the magnetic field. So in this region here, the magnetic field will be concentric rings around that central conductor, and from this viewpoint, they're in the counterclockwise direction. Now, the integral of b dot ds, if we stay the same distance r away from the center all the time, it'll be the same strength of magnetic field. The dot part, b and ds, will point in the same direction if we go in the counterclockwise direction. So the integral becomes the integral around the circle of just b ds, b constant, so it can come out of the integral at a particular radius. And we've got the integral around a circle of ds, which just gives us the circumference of the circle, which is just going to be 2 pi r. So, and r, yeah, r in this case is in between a and b. So we'll have that, and that'll just equal mu naught I. And so the magnetic field within that thing is just mu naught I over 2 pi r. We really didn't need to do this much work to figure it out, because we've kind of figured that out before, except that we maybe didn't know that we could ignore the influence of this outer conductor here, but we can. It doesn't affect the magnetic field inside of this loop. And so if it does have any influence, whatever influence is caused by some current over here will be undone by some current over here. And so the only magnetic field within this region is that due to the central conductor. So we have that. For part B, we're going to have our R being greater than C. So we'll be outside the central conductor in this region here. Well, Ampere's law says this: the integral of b dot ds is going to equal mu naught times I enclosed, the current that's enclosed by the integral path that we're taking here. Okay. We've got axial symmetry here, and so we can use a circular path, but there's no current enclosed, because current in the central conductor is going one direction, current in the outer conductor is going the opposite direction. Those would add together with opposite signs, and they're equal currents, and so this ends up being 0. So this would end up being 0, and the only way this can be 0 is if there's no magnetic field. And so, or if you could somehow contrive a way to make B and DS perpendicular all the time, but you have to do a closed loop, and that's not going to work out so well. So anyway, outside that conductor, there's no magnetic field. This might be advantageous if you've got something that is carrying large amounts of current and you don't want to have a bunch of external magnetic field that can foul up other instruments or electronic equipment. Then you can have a coaxial cable like this with some sort of an insulator between the inner conductor and the outer part. So there's something you could do. Okay, there's a section at the tail end of the chapter that's about ferromagnetism and I don't remember what all they call it, sources of the magnetic field. What do they call it? Magnetic materials. And we don't really need to worry about that very much at this level. And if you take a more advanced course, you can study this stuff. Though one of the interesting ones is something called ferromagnetism and ferromagnetic materials. And actually, they've got some pictures here that things that have ferromagnetism like nickel or iron, there will be little regions within the material where the magnetic moments of all the individual atoms will line up together within that region. But then next to it, there will be regions where the magnetic fields point in other directions. And in general, those things can be kind of random. And so you won't have any magnetism that's produced by that. But if they're exposed to a weak magnetic field, which is center picture here, this is the magnetic field going from left to right here, then the regions that have their magnetic moments pointing in that direction will grow and the other regions will shrink. And in a stronger field, they'll grow even more. And when that's the result, you can end up with a device or object or something having a net magnetic field. I've got a gadget out at school that I use for, I call it rejuvenating the bar magnets that we have out there. We have some iron bar magnets, and you stick it into this gadget, and it's just a thing with some rectangular holes in it, and you put what you want to be the north end of the magnet into one of the holes and what you want to be the south end of a magnet into the other hole. And so you'll have your bar magnet sticking out of there. And so this one would have the south end up and this one would have the north end up. And then you lay a bar of iron over the top of that to sort of complete the magnetic circuit. And you flip a switch and it makes a very strong magnetic field on the inside of this box here by putting a large current through some coils, and you rejuvenate the magnet. You can also do it with things, you can screwdriver in there and a pair of screwdrivers if you want, and then put this bar across the connecting the two shafts of the screwdrivers, and you'll magnetize the screwdriver. And a magnetized screwdriver is a handy thing to have. Like I was using one last week when I was undoing some screws on a computer motherboard. They were little tiny screws and I had to go in vertically, and there was no way I could have reached my hands in there to hold the screw in place. Or to even put it into the hole, but it was a Phillips screw, and by sticking it onto the screwdriver, I could just poke it down, turn the thing a few times till the threads were engaged, and then just screw it in the rest of the way. But they're nice to have in certain applications, especially working with little tiny screws in tight places. They're sort of nice that way. But that's something that you can do with material that has ferromagnetism. Now, sometimes this stuff can happen in places where, well, when stuff is hot, just the thermal motion will tend to make all of these little ferromagnetic regions or domains just randomize. And you can do that with a screwdriver too. If you've got one that's magnetized, if you heat it up with a torch, you will demagnetize it. You don't even have to melt it all the way. Just heat it up pretty good, and it won't be magnetic anymore. But as rocks form, the external magnetic field that's applied would be the Earth's magnetic field. And if they're molten, they're just going to stay kind of random. But as they cool, these little magnetic domains will grow in the rocks. And as the things start to solidify, and even in a weak magnetic field, you're going to have some net magnetism to those rocks. And this is something that sometimes referred to as paleomagnetism. There's a place in the Atlantic Ocean, and this could be the east coast of the United States. I have no idea what the geography looks like in fine detail, but then Europe is over here, and someplace along is Iceland. Well, there's a place running down the center. I can't map out the line, but it's something called the Mid-Atlantic Ridge. And it's a place where, coming from below, the Earth is actually splitting apart at this point. It's converging other places on the surface of the Earth, but split apart very slowly. And new material is coming up from the mantle and spreading out from there. Well, that new material that's coming out of there is in a very hot state. And so it's not going to be, it'll just have kind of random stuff. Igneous rock typically has iron in it, by the way, which is what this stuff would be. However, as it starts to cool, the magnetic moments of those rocks, or the magnetic fields of them, will tend to line up with the Earth's magnetic field. And what they see in the rocks on either side of the Mid-Atlantic Ridge is, on evenly spaced, they'll have the magnetism of the rocks pointing in the same direction, but when they go out a little bit farther, they're pointing in the opposite direction. And when they go out farther still, they're pointing in the opposite direction. And what we know from seeing this is that the Earth's magnetic field has reversed direction at times in the past, every few million years or something like that. And over time, it's produced this kind of magnetic striping effect that's symmetric either side of that Mid-Atlantic Ridge. And it's kind of interesting. Earth's magnetic field is not static. In fact, the location of the North Magnetic Pole is moving. It's up somewhere north of Hudson Bay, and it's moving, kilometers per year. I can't remember what the exact amount is, but it seems to be speeding up in the rate of motion right now. So if you've got a compass, at some point you may have to look up what the correct declination for the compass is. It may have changed since you got your old maps. Used to be on the kind of topographical maps that you'd use for backpacking. Up in the top corner of it would be something that told you what the magnetic declination was for that map. It'd be over a small area, and you would correct for that on your compass when you're doing that, because you want to know the direction to the geographic North Pole, but the compass will point at the magnetic North Pole, and so you want those things. I have a friend who's a geologist, and we used to go camping together every summer. Well, he was exploring sites for possible geology field trips, and there's a spot we've gone to several times down in southeastern Oregon at Steens Mountain, and that's one of the places where they've taken magnetic cores out of the rocks up near the top of that mountain to see which direction the Earth's magnetic field was pointing. And in the rocks on that mountain are not pointing the same direction as the Earth's magnetic field is now. So part of that is due to the fact that those rocks are, as they've been uplifted, they've been shifted around and rotated. But part of the reason is also because the Earth's magnetic field has changed direction. And he sent me an article a few years ago that magnetic field during the in-between times can be pretty chaotic, and the reversals can take place from completely in one direction to completely in the other direction in fairly short periods of time, like as short as 50,000 years, which on a geologic time scale is like the blink of an eye, but it's long for human time spans. But, well, that stuff is chaotic. The protection that we get from the Earth's magnetic field, from solar radiation, and by solar radiation, I'm thinking mainly solar wind, which is the stream of charged particles from the sun, but also, well, yeah, that stream of particles and cosmic rays too. So those things just get to impact the Earth's atmosphere, and lots of weird things could be happening in that during those chaotic times in between the reversals. So it's kind of interesting to read about this stuff. It may seem pretty technical when you're going through it, so don't worry about it. But if you've got an interest in things like that, go and have a look at it. Let's look at some of those demonstration videos and see what those things happen to show us. Okay, Faraday's discovery is the first one, and his original discovery is demonstrated by observing the induced current in the secondary of overlapping coils. So it's probably going to ask me that question on every one of these things.
Hello, I'd like to discuss and demonstrate Faraday's law of electromagnetic induction. Here we have a statement of Faraday's law. Magnetic induction, known as Faraday's law, is that a changing magnetic field or a changing magnetic flux will create an electric field. Faraday first discovered this phenomenon in the year 1831. He was over working at the Royal Society in London, England, and he was working with some coils of wire, and this is the discovery that he came up with. I'm now going to demonstrate that. He had a coil of wire on which he wrapped a secondary coil, which I'll do here in just a minute, so that he had a primary coil, which would be like this yellow coil here, and he had a switch to connect it to a battery, and he had a secondary coil connected up to a galvanometer. So let me go ahead and wire this up, put the secondary coil on it, then we'll connect it up, and we'll do the experiment and see what happens. So now I'm prepared to wind onto this primary coil a secondary coil, which is electrically independent from it. I have previously wound 200 turns primary coil. That's with this lead and this lead being the ends of the primary coil. And now the secondary coil is going to have, this is one end, and when we cut that off, we'll get to the other end here. I'm going to wrap 200 turns onto the secondary coil. So I'll wrap those turns, one.
By the way, that wire is insulated. It's copper wire, but on the outside of it, it's got a thin resin coating. So if it wasn't insulated, instead of having multiple turns of a coil, they'd all be in contact with each other. And you'd have actually, you wouldn't even have a coil really in that case. So 2, 3, 4, 5, 6, 193, 94, 95, 96, 97, 198, 199, and 200 turns. Okay, we'll tie it off here at this point. Then cut the end and clean the varnish off of here. Of course, Faraday didn't have nice wire like this. He had to take copper wire and wind it with string to keep the various parts of the wire from shorting into one another. We have an insulated wire, so the various parts of the coil are electrically isolated from one another. But we need to clean the varnish off the end of this to get a good connection. So now we have the coil in this fashion. Primary coil we're going to connect up to the battery. Secondary coil we're going to connect up to the galvanometer. The primary coil was wound on here first. It has 200 turns. The secondary coil was wound for the top of the primary. It also has 200 turns. Now I'd like to hook up the circuit. We're going to connect the primary coil through the switch to the battery, one side,
and the other side, so that the primary coil, which is the first coil wound on here, 200 turns, will be connected when I throw the switch to the battery. The secondary coil is the coil that's laid over the top of the primary coil in this case, and that'll be connected to the galvanometer, which is a current detecting device. Now the battery is going to pump electrons through the circuit, and when I throw the switch, it'll take just a fraction of a second for that current to build up to its maximum value. It's that change in current that will cause a changing magnetic field that induces the electric field in the secondary circuit, which causes a current to flow through the galvanometer. Let's see what happens when I throw the switch. So when I throw the switch, I increase the current in the primary circuit. That causes a change in the magnetic field, which induces an electric field, which drives current through the secondary part of the circuit. Similarly, if I open the switch, we will see another change in magnetic field. The magnetic field will drop to whatever value it now has, to 0. That's a change in the magnetic field, and that causes a change in the electric field in the other direction, which causes the current to reverse its direction in the galvanometer. So when there's no change in the magnetic field, there's no induced electric field in the secondary coil, and therefore there's no current in the secondary coil. There's no change when the switch stays open or when the switch remains closed. No change. No change. There's no effect. But when there's a change, either opening the switch or closing the switch, we get a change. And to summarize, a changing magnetic field or a changing magnetic flux will create an electric field.
That's important.
Hello, I'd like to discuss
That's important that it's the changing magnetic field or changing magnetic flux that induces the electric field, not a constant magnetic field or constant magnetic flux. This one's all about change. Let's see. Oh, where did my list of things go? I don't know. Oh, I guess I can click back. That should do it. Oh, this is an even more primitive demonstration of this. This is usually the one that I start with. It's just a magnet in a coil and moving a magnet in and out of a coil to see that effect. And I need to drag it back over and blow it up. And yeah, this is the demonstration I usually
Next, I'd like
start
to
with.
demonstrate another example of Faraday's law of electromagnetic induction, which is that a changing magnetic field or magnetic flux will create an electric field. Here I have a coil of wire, and I'm going to hook it up directly to the galvanometer in this fashion without a battery or anything else in the circuit. This is essentially the circuit we have here. We have a coil of wire wrapped on a spool, and in this case it's hollow, so that I can then insert the magnet into the center of that. And when we insert the magnet into the center of this coil, the coil will sense a changing magnetic field. It's a magnetic field that wasn't there to start with as we introduced the magnet into the coil. So a changing magnetic field will create an electric field in this coil, which will then current through the galvanometer in much the same way that a battery will drive a current through a circuit. So let's see what happens when I take the magnet and insert it into the coil. Now let's watch what happens when I pull it out. Opposite direction. So an increasing magnetic field will cause an electric field in one direction to drive the current through the circuit in one direction, deflect the needle to the left, and a decreasing magnetic field will do just the opposite. Now I'd like to reverse the magnetic field, and we see in that case it causes an electric field change in the opposite direction. And again, when we reduce the magnetic field, that causes a change, and we see that a changing magnetic field creates an electric field, which then drives a current through the circuit. Next, I'd like to demonstrate another example.
Whoops. Every time I click play, it rewinds automatically. That's a a simple demonstration. What he did to reverse that was if he'd pushed the south pole of the magnet into the thing first, when he flipped it and pushed the north pole of the magnet in first, he did that. And we'll learn how to kind of analyze that situation in the coming days and know which direction the current is going to flow in the circuit based on which end of the magnet we punch into the thing. But again, when you just have the magnet sitting inside the coil, there was no current flow. It's only a changing magnetic field that causes this effect. Let's see. The transformer, he actually built one there, but in the first video that we watched, or the second video, I've lost count. So far, he's been either using direct current or just that of a magnet, but now he's going to start using alternating current. And alternating current is what we have our wall power, so you can see what's going to happen in this case.
Another application of Faraday's law is the transformer. Here I have the primary coil of the transformer wrapped around a vertical cylinder here, and with an iron core down through the center of that vertical coil. That coil is connected through a switch to the power source, which is 110 volts, 60 cycles per second. So what's going to happen is the current is going to change at the 60 cycles per second. That's going to cause the magnetic field to change, first up and then down and then up and then down 60 times a second. The purpose of the iron core in here is to enhance the magnetic field and there enhance the rate of change of magnetic field. Secondary coil is going to be this circuit here. We have some wires connected in a series circuit through the filament of the light bulb, and just a continuous circuit here. So this is the secondary coil. When the secondary coil is then brought up near or in the vicinity of this changing magnetic field so that the magnetic field actually penetrates the secondary coil, we're going to get a change in the magnetic field that the secondary coil experiences. That's going to cause an electric field that's going to drive current around through the circuit, and in particular through the light bulb. So when I push on the switch here, that turns on the current, the changing current to the primary coil, changing at the rate of 60 cycles per second. Magnetic field is changing. Changing magnetic field creates an electric field. When I bring this close enough to where it can sense that changing magnetic field, then we see the light glow as the electric field is produced in the secondary coil due to a changing magnetic field, due to a changing current in the primary coil.
Okay, that one's pretty neat too. I took a couple of electronics classes when I was in high school, and in the very first electronics class I took, I think I was in, let's see, I think I would have been in 10th grade, because it was, we moved from an old high school, ancient high school, to a new high school between 10th and 11th grade. But I can remember one of the things that we did in that class was each of us made a transformer, and we were supposed to have a transformer that was a step-down transformer where it would be getting 110 volts out of the wall, and it was supposed to step down to, I think, 7 or 10 volts or something like that. And our test of our project was to see how close to 7 volts we happened to get, or whatever it was supposed to be. And so you had to count the turns that you put on the thing and be very consistent about the way you wrap the turns around stuff. So that was quite the project anyway. Let's see. I may save some of these for another day. I'm curious about this hand generator one. Yeah, open with QuickTime.
application of Faraday's law is this little hand generator here. Now, here we have some magnets. And so in this region of space down here where the coil is, you can't see the coil, but there's a coil in here, which I'm going to rotate. When I turn this crank, I'll rotate that coil in that magnetic field. And so that coil will see a changing magnetic field and therefore create an electric field, which can be translated to a voltage, which will drive a current around through the circuit. Now,
this is a very primitive version of what's going on in our local dams. They've got generators that rotate coils in the present magnetic fields and generate electricity that way, but they're much more efficient than this one happens to be.
Now, the coil is connected one end to one side of the light bulb, and the other end to the arm of the light bulb through this socket here, so that when I turn this crank, we'll generate an electric field, and depending on how fast I turn it, that'll determine how much change there is in the magnetic field that that coil sees. Time it flips over first one way and then the other. So as that coil rotates around there, if I turn it fast enough, I can actually generate enough of an electric field that it translates to about 60 volts of voltage, and it'll make that light bulb glow rather brightly. If I turn it slowly, then a dim glow on the light bulb indicating a small voltage and a small electric field created because the magnetic field is not changing as rapidly. The faster the magnetic field changes, the greater the change in the magnetic field, the greater the EMF is produced and the greater the current flows that flows through the circuit. Again, a changing magnetic field or magnetic flux will create an electric field.
Okay, let's see, do I still have that thing up? He keeps talking about a changing magnetic field or magnetic flux, and that's something that we haven't introduced yet. Back when we introduced electric flux, when we talked about the flux of an electric field, it came from an electric field that was penetrating some area. And if we imagine a little area that looks like this, we could have either defined vector A that points that way or something like that. But this area vector here will be equal in magnitude to the area of this area, area of that area, and it points perpendicular to it. So we'll imagine that this is just some little infinitesimal chunk of area, and the electric flux through that, if we had a uniform electric field penetrating this little tiny area here, then the electric flux was equal to E dot A. Okay. Well, magnetic flux is going to be the same thing. The flux of a magnetic field is just going to be B dot A. And if you want to make it possibly more general, you could extend it to the idea where you've got possibly a changing magnetic field, and you might take a B dot dA over some place with a changing magnetic field, and you just take into account the fact that the magnetic field was different for all the little different dAs in some area. Now, when we used Gauss's law, we put a circle on this thing because we had a closed area. But in this case, it doesn't have to be a closed area. It wouldn't in this case if you just wanted the flux of the electric field. But this only works if you have a uniform electric field and a nice flat area. But if you have something that's not so uniform, you might have to integrate in order to figure out what the electric flux through a surface happens to be. But for Faraday's law, what he found was that if we imagine that there is some just circular loop, and this could be, I guess, a Faradayan loop or something like that. I've never heard that particular term applied before, but this will just be some area. And if there's, say, a magnetic field that is pointing into this thing, then there might be some kind of B dot A, that magnetic flux that is going to be through that area. And he found that if this flux is changing, there would be an induced EMF. And so if you wrapped a wire around this thing, around this area, and maybe had a galvanometer on it or just an ammeter on it, that there would be a current induced in this region or in this coil as if there was a magnet in that thing. And the magnet, or in this case, it's going to be an induced EMF. And EMF is short for electromotive force. It's a term that's hung around and hung around, even though it's kind of bothersome because it's not really a force. It's something a little bit different than a force. It's sort of like an electric field. It is actually an induced electric field, but it's the result of an induced electric field. In this case, the induced EMF ends up being a line integral of E dot ds integrated all the way around a loop, all the way around this particular loop. Now, back when we were looking at things like this before, if you started at one point in space and integrated all the way, integrated the electric field all the way around that thing, you would always get zero, because you're coming right back. The electric field was a conservative field, and that's how we defined electric potential. But in this case, there's something weird going on where integrate around the loop and you get something non-zero, but it ends up equaling this. It'll be the negative of the time rate of change, I didn't do that one very well, of the magnetic flux that's in that circuit or within that area of that circuit. And so this is pretty weird, and that's what we're going to start on tomorrow, is this idea. This is Faraday's law, by the way, and in a mathematical expression. I'm not sure Faraday actually expressed it mathematically. Faraday was self-taught, and he actually got a lot of his education while he was working in a bookbinder's shop. The books that came in to be bound, he would read many of them, and then started going to public lectures and pretty much educated himself that way. But he had this incredible intuitive feel for looking at demonstrations of electricity and magnetism and coming up with kind of verbal descriptions of the way things that were behaving that other people could translate into mathematics. And he ended up being right a lot of the time. And so a lot of what we have for electricity and magnetism equations were expressed verbally by Faraday and then later translated into mathematics, sometimes by James Maxwell, actually. So those are things that'll happen. But we'll start investigating this tomorrow. I've posted a new homework assignment that'll be due next Tuesday, and I'm kind of aiming as that day for our next test. So just sort of plan on it for Tuesday, although I didn't make the homework due until midnight on Tuesday. But if we have the test that day, you would definitely want to take on this homework before the test, because it's going to prepare you for it. And I'll be sending out something about the makeup test to have today. I just didn't hear from many people who wanted to do it, only 2, I think, or Actually only one, but that's okay. We'll see. So watch for that. And I'll stop the share here and see you tomorrow. And I'll be working on the lab stuff for you today too.